Nuclear reactors use the heat from nuclear reactions in the nuclear fuel to boil water. Just as in conventional power stations, the steam from the boiling water makes a turbine spin, which in turn makes a generator turn. Unlike conventional power stations, however, nuclear power stations do not release carbon dioxide, so they do not contribute to global warming while in use. Components of a nuclear reactor. There are several components common to most types of reactors. Fuel. Uranium is the basic fuel, usually pellets of uranium oxide, that are arranged in tubes to form fuel rods. The rods are arranged into fuel assemblies in the reactor core. Moderator. This is the material in the core which slows down the neutrons released from fission so that they can cause more fission. It is usually water, but it may tend to be heavy water or graphite. Control rods. These are made with neutron-absorbing materials such as cadmium, hafnium, or boron, and are inserted or withdrawn from the core to control the rate of reaction, or to halt it. In some PWR reactors, special control rods are used to enable the core to sustain a low level of power efficiently. In fission, most of the neutrons are released promptly, but some are delayed. These are crucial in enabling a chain reacting system. Coolant, a fluid circulating through the core so as to transfer the heat from it. Pressure vessel or pressure tubes, usually a robust steel vessel containing the reactor core and moderator/coolant, but it may be a series of tubes holding the fuel and conveying the coolant through the surrounding moderator. Containment, the structure around the reactor and associated with steam generators, which is designed to protect it from outside intrusion and to protect those outside from the effects of radiation in case of any serious malfunction inside. It is typically a meter-thick concrete and steel structure.
First, we have an isotope of uranium-238, uranium-235, which is the fuel of the fission process. The uranium-235 captures a neutron, which may cause fission. Low-energy neutrons can only cause fission in odd-numbered atomic numbers of isotopes. When uranium-235 has an additional neutron, it becomes the unstable uranium-236. This will break down into krypton-92, 3 fast-moving neutrons. These fast-moving neutrons move about 7% at the speed of light, which is about 2.1 times 10 to the 7 meters per second, while moderated neutrons slowed down by heavy water move at 8 times the speed of sound, which is 2,400 meters per second, and also barium-142. One fast-moving neutron is slowed down by heavy water, which is essentially water, and is used to cause a new reaction. A control rod is used to absorb the other 2 neutrons. A 1 million kilowatt coal-fired power station consumes about 3.2 million tons of black coal each year, and its nuclear counterpart will consume about 24 tons of uranium. In 2011, some 52% of world production came from just 10 mines in 6 countries, these 6 providing 85% of the world's mined uranium. Nuclear power plant workers are at constant risk of radiation poisoning. Nuclear power plants must therefore have safety systems such as good ventilation systems to ensure that exposure to radon gas is as low as possible, efficient dust control, as the dust may contain radioactive constituents and emit radon gas, the use of radiation detecting equipment in all mines and plants, often including personal dose badges, and the imposition of strict personal hygiene standards for workers handling uranium oxide concentrate. These are in addition to measures such as placing nuclear power plants far away from residential areas. In addition to workers' health, there is the risk of chain reactions occurring if the control rods are disabled. For example, in Chernobyl, 90,000 people were killed due to radioactive effects after the recent nuclear disaster at Fukushima. 136,000 people were displaced from their houses and towns and still are displaced.